Hi, in this tutorial we're just going to have a quick recap of the substitution reactions, and then I'd like to talk about the elimination reactions. So if you remember, in the substitution reactions we had SN2 and SN1 type of reactions. There are other types of substitution reactions as well which I will cover, but I just want to stick to the basic ones for now. So if you remember looking at the SN2 reaction, if you've got a chiral centre and it's being attacked in a nucleophilic addition like this, then if it goes via SN2, then you'll get inversion of the stereochemistry, and we can test that by looking at the how plane polarized light is rotated. If you compare that to the other mechanism, which is the SN1 reaction, in this example what we've got here with 2-bromobutane, we'd leave the bromide would leave first to expose the carbocation. The carbocation would be flat in structure, and I've just scrolled down here a little bit, and if you remember, a bit more, if it's flat in structure, then the nucleophile can attack from either side because it can't really differentiate between one side and the other, and you end up with a racemic compound where you've got a mirror image of a chiral compound in the end. So that is the substitution reaction, which we've already covered, so I won't dwell on that any further. I'll just delete that actually. Delete that and scroll down and delete that little bit at the bottom. Okay, I'd like to just cover elimination reactions now. So there are several types of elimination reactions. There's the E1 elimination reaction, there's the E2 elimination reaction, and I'm sure most of you have covered them before. There's the EI elimination reaction, which we'll have a look at today, and there's the ECB, or the conjugate base mechanism as well. Now I'm going to just cover these reactions for now. This is not that common really, the conjugate base. I'll try and cover it at the end if I can. If not, I'll leave, especially these two. These are quite, well, I would say quite rarer than these two anyway. But I'll cover this one because it's quite a good one, and it tells you a little bit about how elimination reactions actually should proceed as well, with the syn and anti periplanar arrangement of protons and leaving groups. Okay, so let's have a look at the first one, E1 elimination. So E1, if you remember from the other the substitution reaction mechanisms, the 1 just means unimolecular, which basically means there's one species present, and the E just means it's elimination. So let's draw some molecules now. Enough talking from me. So a good example of an E1 reaction would be CH3, 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 Br. Okay, and I know this will go quite well, simply because what happens if I just change the colour there. First step for an E1 reaction would be the loss of the leaving group. In this case I've got bromide. That can be any leaving group. For a leaving group to be good, good leaving group, it's got to be quite stable in solution. So what happens after that? If that leaves, well then I'm going to just leave one of the protons off here. I'm going to use this as an example. Obviously all the protons, or the hydrogens should I say, are the same, identical. CH3, CH3, whoops, and that leaves a positive charge there. Very similar reaction mechanism to the SN1 reaction, if you remember. If you've not covered the substitution tutorial, I urge you to have probably a quick look at that before you look at this one, to be honest. So you get this intermediate where the chiral centre of its chiral is scrambled. Obviously this is not chiral because it's got no asymmetric centre in the molecule. Now this is the slowest step, and if you if you remember, the slowest step is the rate determining step for the whole reaction rate. It tells you how fast the whole reaction will proceed. So if we got this carbocation here, and it can be either attacked from either side by the nucleophile. Now we've no base in this at the moment, but we're going to put a base in, and we'll I'll stick with this base. It's quite a strong base. Okay, it's the methoxide ion. Methoxide. Just write that over here in blue or green. Methoxide. And these are usually performed in aprotic solvents. Aprotic solvents. And a good example of that is dimethyl formamide, which is what most people use. Which is this compound here. This is a formamide bit there. So that's a formyl group. If you've done functional groups, then this bit here is called a formyl group. So that's a formamide, and it's dimethyl formamide. So that's how we name that compound. Okay, so we've got a methoxide in some aprotic solvent. It doesn't have to be DMF, it can be anything really. As long as it doesn't provide a proton source, because this would pick up the proton, you see. It'd react with the solvent. You don't want that to happen. So we've got a very strong base, but the base hasn't actually done anything yet. In fact, the base doesn't need to do anything. It just needs to mop up the acid at the end. So we don't need a strong base in this case. All we need to do is drive the reaction forward. So what happens now, the second stage, is you get loss of your proton to give you a product. But I'm going to go back to this molecule in a minute. It's very important this for the whole E1 mechanism to proceed, is the stability of this molecule, this intermediate, sorry. And that will give us okay, and you've got your two hydrogens stuck on there. So that's your product of the reaction, an alkene. Okay. Now let's go back to this. Let's just drag that out. Let's just grab that, copy it, and just put it over here. If I can, I'll drag a bit of that out. Doesn't matter. Right, let's get rid of that. Let's have a look at this now. This is what is driving the E1 reaction. This is the most important bit, the stability of this intermediate. This is the whole reason this can fall off. This only falls off if this is stable, otherwise it won't let go of those electrons. And one of the reasons it's stable is because it's got, now you'll see this several examples of this, and several explanations will be, oh, these alkyl groups push electron density into that positive charge there. So the more alkyl groups you've got around that positive charge, the more stable it is. So if you, for example, drew CH3, and that's a positive charge there, that's a hydrogen there now, CH3 plus, that will be less stable than this one because it's got an extra, and similarly that would be less stable. Okay, so if we replace these methyl groups with these hydrogens, it becomes less stable because of less. There's fewer alkyl groups pushing electron density in. But really, what does that mean? Well, it is a bit too advanced for this tutorial. But I will mention the word hyperconjugation because that's something that people tend to mention quite a lot, especially in first year undergraduate studies. Hyperconjugation. Okay, and basically this is remember, this is a vacant orbital, so this is like an empty bucket of water. There's no water in an empty bucket of water, so it's just an empty bucket really. So it's an empty, but this has got electrons here, and these just happen to be quite aligned to this orbital here, or the empty space, and they will push electrons into it like that. In a way, if I draw it like this is your try and draw it in 3D. Now I am digressing a little bit, but I think it's very important actually sometimes to explain why things are stable. Now the orbital there, if it's gone flat, if you've done orbitals before, will be more sp2 like. So these are like sp3 orbitals, or hybridized orbitals. And you don't need to worry too much about them, but this is basically the shape. But let me draw the other CH3s on there. And what we've got on here, we've got hydrogens on here. So that's going to be H. And this is like a natter drawing. If you've ever seen them before, this three-dimensional representation is sometimes referred to as a natter projection. Right. Okay, so what's happening here is we've just got the electrons. Remember, the electrons are negatively charged. We've got this empty orbital, so this carbon needs to complement its electrons. So basically, that shoves electrons, or like almost shares electrons with this, and we've got all these hydrogens that are spinning around their axes there. Okay, they're spinning around, so now and again there's got enough orientation. The orientation is right to line up with that, put in the electron density, and that's basically hyperconjugation. Really, it's a stabilisation from the alpha. These are the alpha positions, alpha carbons there. Okay, and they stabilise the positive charge. So that is really what is making this a stable species. That is what's driving this type of mechanism. Okay, the stability of this carbocation. That's a cation, yeah, carbocation. Okay, but that's going into detail. The key message is you need to stabilise that intermediate there. If that's stable, then it probably proceed by this mechanism, and because only one molecule is involved in the slowest step, it's called E1. Okay, so that's an E1 mechanism. You don't really need that strong a base, because the slowest step is this. You just need stable species. Okay, so that's E1. Let's have a look at E2. We'll try and use similar kind of molecules if we can. So I'll just get rid of these. Delete that.